Hey there, Calc folks, back here with what is hopefully a successful demo. I'm having some tech issues. I recorded, an hour and a half of videos over the weekend and did not have my mic turned on. Somehow it got turned off in my recordings. And then the software I'm using to record everything recently updated with all the Windows updates. If you got a new Windows system, it updated in the last couple of weeks, and I finally updated mine last Friday, and ever since I'm having some tech issues now and again. So, I'm trying to survive with all that. I got to figure this out, but I'm not able to get my title screen to come up at the current moment. But that's not going to be a big deal. What I did lose was an hour Mathematica demo that I want to go back and make sure that I put together for you folks. Can't have that go without sound. Where I am picking up from last time, and I'll get right into it because I did lose an hour of time on this, and I don't want to spend another hour doing this if I don't have to. And I've been through it once already. So I know where all the little bugs are, and I should be quite familiar with this program up to this point. So going forward, hopefully I can speed this up a little bit. Go ahead and open up your Mathematica if you haven't done so already. And I did write a program for you last time. This program here for plotting multivariable functions and doing a little domain analysis. And what I'm going to add on to that this time around is with level curves. Right? We're going to add some level curves. And this is going to allow us actually to go a little further and actually look at some limit analysis also. All right. One of the first things, though, I want to make sure that I mention in this video is up here I'm gathering up some practice functions, and I might go ahead and write another practice function up here. And you can do this with yours program individually, folks, as you can declare some practice functions. But maybe I declare the practice function 4 minus x squared minus y squared in value, folks. And if I wanted to then come down and use that function in my program, I would declare its name down here in my adjustables for function f, right, for my practice list. But now, this was not part of the original program. Let me get rid of that. But I don't have a constraint concern. If I leave those blank, however, when I go down and look at what they plot in terms of a graph, yeah, I gotta get rid of something else in here. I got a couple of commands left over from the first time around when my sound wasn't working. So I want to make sure I get rid of all of that. But yes, if we go to try to plot this, we don't really get a domain illustration. All right? We don't really have an illustration of the domain. It's all real numbers. It leaves it blank. Right? But I would like it to show something. So what we can actually add up here in our constraint when there is no constraint is we can declare that x is an element of the reals and y is an element of the reals. And that is a safe declaration. What we do see is we do get a nice little region down here that becomes shaded that shows us it's everywhere. It exists everywhere. Right? When there is no constraint, we can leave the constraint function blank. Right? There's going to be no boundary on our constraint. Right? With some constraint function here. And I do want to add this to the notes here, or into the documentation, so we don't lose track of that. What we might say here is, if no domain concern, use that statement there, so we can just copy and paste that over, folks. The statement seen here. Right? We'll just be able to copy and paste that over. And then we'll just leave none here. If no domain concerns, leave blank. All right, we should be able to say that and understand that. All right. Now, what we are going to want to do in these domains, though, this illustration of the domain, is plot our level curves. All right. We could plot a single level curve. Maybe we want a level curve at a level of z null equal to, maybe we go with the level curve at 0 in this case. All right. And the way we're going to have that level curve appear, I'm going to do a little level curve analysis here, right, in my program. And the way we're going to plot this level curve, folks, where z null equals 0, is we are going to solve for when our function at x comma y is equal to z null, right, with respect to variable y. We can see it does give us this solution seen here. That is that solution, all right, for when z is equal to 0. Now, it does give us kind of that funky solution there where it says y can be replaced with this and y can be replaced with that. Right? To actually clean up that solution a little bit, we can go in front of the solve and say, yeah, let's take y and let's replace it with those solutions. And now we can see that we actually get the nice solutions there. Right? Where I'm going to want to plot those now in my coordinate system. Right? And the way I am going to plot that is I do think I can just do a plot 3D on that, if I'm not mistaken. I can do, no, well, sorry, not a plot 3D, just a plot of that over values of x from a to b. Is that going to work for me? Okay, it will give me that plot scene there. Now I want to lay that into my domain illustration. My domain is called plot 0. Plot 1 is my constraint function if it was to exist down here. Right? So what I'm going to want to lay in here is plot 2. We're going to go up here and call this plot in our level curve analysis. Plot 2. Right? And another thing we might do is go ahead and let's change its plot style slightly. Let's do a couple of different plot styles in one. So we're going to do a directive here, command, where we're going to call out red as one of the directives, and then we're going to make it a little thicker in its graph. Right? So we get that illustration of our level curve. Now certainly let's zoom out of our picture here. Let's zoom out to, maybe negative 10 to 10 for A, and maybe negative 10 to 10 for Y. That might give us a slightly better illustration of our level curve in there. All right, a little easier to see in that domain space. Let's turn this off by putting behind that plot a semicolon. That'll now turn off that output. All right. We're still getting this constraint to read. Where's that coming from? I believe that's coming from right here. We can turn that off if we felt the need. And let's turn this off up here. All right. So this is the function we're analyzing, and this is the level curve of that function, right, at z equal to 0. That's the case for z equal to 0. Now, if I want to put in some more level curves, right, one level curve really doesn't show us that much information. We might want to have more than one level curve. So let's do that. And the way we're going to lay this in here, folks, is we're going to actually we're going to have our number of levels. We're going to actually set our number of levels above or below this null value. So maybe we're going to set this initially for 3 levels, and then we're going to set a del z. Del z is going to be the difference between each level, and maybe we'll make that initially the value of 1. All right? And we're going to write this so that we're going to center ourselves in our level curves at z null equal to 0, and we're going to look at 3 layers above that and 3 layers below that in level curves, where the difference between each layer is this del z value. Now the way that I am going to do that is I am going to make a table of solutions. I am going to make a table of those y values that are going to come out of a solve, where we are going to solve f at x comma y equal to now what would be the solution in this case. Let me scroll up so you can see this. Remember, my scale here in my video is a little less than what I have here, folks. All right. What actually might help me with that scale, let me, because this doesn't change anything until I bring that all the way down there. So as long as I stay in that picture, I should be able to stay within scale with you folks. All right. So if I do that, we're going to look at this solution at a particular, well, at a variety of solutions. We're actually going to set it up so that it looks at all the level curves around z null, 3 below up to 3 above, all with a difference of 1 around this value is 0. And the way I'm going to do that is I'm going to just call this S. S for solution. Maybe we call it a big S for solution, right? And we are going to want a table big S values starting at a lower bound. Now the lower bound is going to be my z null value minus my number of levels that I want, right, times the difference in each level, del z. And what that is because we're going to be subtracting this away. We're going to be subtracting 3 levels away from z null down below it. We're going to increment up our values of S starting at this lower bound and continuing up through this upper bound, where we see kind of a similar calculation where we take z null, but we're going to add in our number of levels here. Times our del z, the difference in each level. And we want it to increment by the difference in each level each time, by del z. Now, if I run this table, what you will see is we get a table of all the solutions for all those level curves in this illustration. All right. It actually goes off the page here with my illustration. You can't quite see it to the right. All right. If I was, what I want to do with those folks is I am going to want to plot them. All right. And the way that I'm going to go about plotting them is I'm going to gather them all into a single set. Right now they're in a bit of a matrix. They're in a 7x2 matrix. 7 sets of 2. So it's a 7x2 matrix. We want to basically get one set of 14. And the way I'm going to do that with this here is around that table, I am going to run one more command. I'm going to run the command flatten. You'll notice what flatten will do here for us, folks. If I wrap my table in a flatten command, you'll notice how that changes our result here. Right? It takes each of the elements in that 7x2 matrix and just arranges them in a single array of 14 elements. Right? Puts us in a 14x1 vector. Right? The single array of elements. Now what I'm going to do with this single array of elements is I am just going to plot them. Again, we're going to come along and plot them. Right? We're going to plot them over values of x back here in the end, from A to B again. Let me give myself a little room here. All right. We're going to plot those, right, for values of x from A to B here. Now, if I make that plot, it will just sketch that plot all by itself. It didn't even sketch the plot. Where did I go wrong? Flatten table, x values. Where did it go wrong? Let's see here. No? Why is this not working? Well, let's do it this way then. What I probably should have done is, let's go ahead and call this a table. It's our first table. We'll call it T1. Now that cleaned things up a little bit. All right. We'll call it T1, table 1. We will plot table 1 over values of x from A to B. That might be our issue. Let's see if that fixes things. Yes. So we end up with all those level curves plotted individually. I can come over there and put those into my graph, right? By making that another plot. We'll call this plot 3. And we can layer plot 3 into our domain here. And I'm actually going to layer it in between plot 1 and plot 2 because I want plot 2 to lay on top of it. Plot 2 is red. Plot 3s are all different colors currently. We're going to make them blue. And I want the red one to lay on top of the blue ones. There's one blue layer that actually matches up with the red layer, but I want the red layer to kind of highlight that Z-null location. So I'm going to layer plot 3 between plot 1 and plot 2 here. Now if I run that, it becomes a little bit of an uglier illustration here. And in fact, I might zoom in a little bit. Let's go into -5 to 5. -5 to 5 for our bounds here. All right. We could turn off this plot that we're making, this plot of that table. All right, so we just get the plot in our domain. What's going on? Oh, here it is. Right. Now all those plots are going to be plotted out in different colors. Let's make them a single color. Now you can see what that red layer is layering in there. There is a plot underneath there, but we're layering in on top of it the red graph by changing that order there in that show command. If I was to take out the P2, you would actually see there is a blue layer right there. Right? Or not a blue layer. There's a 1, 2, 3. It's this yellow and blue layer right here. There is a layer there that I can cover up with that entirely red graph by layering in plot 2 above it. Right? So I do that here, folks. Where then I am going to come back to these plots, and let's just go ahead and make them just blue. We don't really, I think, need to change their size at all. So we don't need a directive command. And notice there's our level curves. There's 3 levels above and there's 3 levels below this level that's marked in red, which is the level at Z0. Right? Equal to 0 in this case. So some of these levels are at 1, 2, and 3 for Z, and -1, -2, and -3 for Z. And their levels up and down the space, that third dimension. All right. Let's see here. What I might want to do with those, let me actually, one thing I do want to do, there's some leftovers still from the last program run. Let me clear that kernel. Let me delete all my output. Let me do one fresh run here. See what I get in the end. I'm still getting the level curves plotting in there. Where though? No, wait, they disappeared. No, they're still plotting in there. Well, this curve is left over from somewhere else. Why does that keep dropping in there? Let's get rid of that. That's why I keep seeing that. That's left over from what's going to be the final product here before I lost it all with my sound issues, folks. All right. You'll notice both the box ratios here are a little off, right, with these 3D plots. Well, first of all, what we want to consider doing here is, what do these level curves look like on our surfaces? Where would these level curves be positioned at on our surfaces? And that's something we might consider adding to these graphs, right? Is where would these level curves position themselves at on these surfaces? So we're going to add that into our program here in our level curve analysis. We're going to add in a little bit more that's going to tell us where those level curves are positioned at, right, on those three-dimensional surfaces. And then we're going to lay them into the plots of those three-dimensional surfaces. Let me go over and check that code real quick so that I can make sure that we get through this here in a timely manner. But let me flip out of the screen for just a second, and I'm going to pause it. All right, folks, I'm back here. Let's see what we want to do with this code. We're going to, my plan is to take these level curves and plot them onto these surfaces so we can see them as these curves upon the surface, right? Actually see the slices, the cross sections on the surfaces themselves. All right, these different layers of Z appearing on these illustrations, right, in these three-dimensional surfaces. The way we're going to do that is as we plot any graph or curve, I should say, to plot any curve in three-dimensional space, we have to use a parametric plot, right? What we're going to plot is a parametric description of a curve in three-dimensional space that is going to be located at an x value of x, a y value that is going to be the first, well, is going to be table 1 values, right, at our different values in that table, right? Here, I'm just going to show you the first one. If we were to look at just one of them, right, one of those vectors would look like this description here. All right. This is 1/2 of one of these circles graphed out in the three-dimensional space, the layer where Z null is equal to -3 in value. How did I find that? Well, I just let x be x in that equation. I let y be -square root of 7 minus x squared. And I know the output of our function at those two locations is going to be -3 for every single value of x. And that's what this is giving me as an output. All right? But I'm not going to want to just do it for this first half circle. I want to do that for every single observation in this table of solutions that are giving me these half circles in my plane here. Right? And the way I'm going to do that is with a table. Again, this is what's nice about Mathematica, is we can make a table. And what I'm going to be changing in this table are these table values. Now, this is table 1's first value. If I was to change that to 2 in this notation, that would be table 1's second value. And you can see there it used the second value. If I was to change that to a 3, that notation would be using table 1's third value. Right? This third value in table 1. And so forth. What I'm going to want to have this do is do this for S values. Right? For S values in a table, starting at 1 and going up to the length of whatever t sub 1 is. Right? And table up those values. And we build this huge, pretty good sized table of parametric curves. Here's the first one we found. Here was the second one we found. Here was the third one we found. And this went through and found it all for all 14 of them individually. Now, like we did with the other case, we're going to want to call this a table. We'll call this table 2. Let's go ahead and turn it off. We don't need to see it each and every time. And in fact, let's go up and turn this table off. But we're going to call out a plot 4. And we're going to plot, and this is going to be 3-dimensional, and it's going to be parametric. So this is going to be a parametric plot. 3D of table 2's parametric descriptions, right? There's 14 of them there, all with X, Y, Z values in their descriptions. That's going to happen over values of X from A to B. Now, if I graph that, here's all those graphs, those parametric curves just off on their own. We need to actually drop them onto the surfaces. Right? So how we drop that onto the surfaces is, now notice that we haven't named our surfaces. Let's come down here and call this first one P null 1. I already got P null. That's the domain plot. That's the region plot up here is P null. So let's call this one P null 1. And we'll call this one P null 2. We're going to turn these off because we're going to gather these into some show commands. We're going to show P null 1 with our plot 4 that we just made. And then let's do that here with P null 2 also. Let's show P null 2 with our plot 4 that we just made. All right. We still got that showing up. Let's turn that plot off, plot 4. We don't need that anymore. Let's turn that one off. Where's that at? That's up here. So we put a semicolon behind that. We can turn that off so it doesn't get so cluttered. But here you go. You can see it on this graph. There is our level curves, right, being plotted onto that surface. And then here's the parametric description of that surface with those level curves being plotted on. Now, both of these are doing a rather poor job doing any scaling, I would argue. Both of these do a really bad job scaling. What we could do with these two plots is we could add in some scaling ratios. We could do box ratios that are automatic, which sometimes works nicely. Some graphs work nice with automatic box ratios. Some don't. Now what automatic does is it does put everything into scale though. All right. So that graph is an appropriate scale, and you can see both of them look the same because they both should be illustrating proper scaling in all dimensions. Proper scaling isn't what we always want. Sometimes we just want to see overall shape. So box ratio 1:1:1 sometimes works really well. Right? Make it 1:1:1 in all three directions. Right? And you get a nice overall box that's what, rectangular or square in shape, cubic in shape. It's 1:1:1 with its dimensions. Right? It's 1:1:1, we say, in ratio with side measurements or dimension measurements. And both graphs show those level curves being plotted into our space. Now, those match up with the level curves we see here, except we don't see the red level curve. We got to get the red level curve in there. I want that red level curve in there. So the way we're going to get our red level curve in there is kind of like what we did up here. We actually put this solve command inside that plot. That we could have left it out. That would have helped us in the next step. Maybe make our program a little cleaner. But I am going to solve again there. F of x comma y equal to 0 for y. Right? I am going to want to declare these solutions with a y being replaced with. Right here they are right here. And what I want to do with those now is drop those into a parametric equation. Yes. As I had done earlier. So I'm going to call these out as table 3. They're almost their own table if we want to think about them. And then we're going to come down here. And we are going to... excuse me. Let me check my code. Will they work as their own table? I still think we have to... Well, we still have to make the table of parametrics, though. Yes. So what we end up doing here is we're going to make a 4th table, table 4, which is going to be a table of our parametric descriptions for these values. And really it is just going to be x, comma, table 3's first and second value is what we're going to select. And they're going to have an output at z null. So we can be brief there. And then we're going to have this cycle from s values from 1 to... Let's be careful and just call this out as the length of T3. Now you can see it's going to make those parametric descriptions of that red curve in 3-dimensional space. Where I'm now going to plot that parametrically. This is going to become plot 5. It's going to be a parametric plot 3D of table 4 values over values of x, again, from A to B. We do get that curve layered in there. Now, we do want to change its color. Let's turn it off. Change its color. Let's go plot style. Directive. Again, we'll go red. And we'll add some thickness by just saying thick. And then let's lay that into these plots down here. Right? Let's lay that on top of P4 in both of these. So it'll stand out on top of its corresponding blue ring, right, in these illustrations. So this should match up with this illustration down here. Right? Respectively. Now, one thing I like to do also is with these box ratios, I am going to be changing these every now and again. So let's do a box ratio setting. And let's bring that up top as a adjustable. So let's put that in right here too. Box ratio setting. And let's come up here. And let's say our box ratio setting right now is set on a 1, 1, 1. But we could also adjust that to automatic if necessary. All right. That gives us that plot. If we want to look at a different surface, right? Maybe we want to look at surface G. We can look at surface G by changing our adjustable F to G. We are going to have a little constraint here. Right. We'll go about changing that constraint over. What has to be true there is that has to be greater than or equal to 0 in value. That is going to be my constraint function. Are we going to include it? Yes, we can include that because we can equal 0. I think that might work. Let's see what that gives us. Right. The level curves aren't quite as visible, and it's because we're kind of lower down on the level. Notice this whole surface just exists above because it's a square root. It's only going to be positive for z's. And I'm looking at z equal to 0. So let's raise our z null value. Maybe we raise our z null value up to, let's raise that up to a height of 4. That'll capture all 3 layers rather nicely. And then let's bring, well, let's see what that looks like scale-wise. Right, yeah, we get a nice illustration there. Here's our level curves plotted in the domain. Here they are down here plotted on our surface. Now, why aren't those laying in exactly? The red ones aren't laying in exactly as they should be. I'm off somewhere. Where am I off at? Looks like my Y values are off somehow. Ooh, where's my bug? T sub 3 of S. Oh, right, here's my bug. I need to have that set at Z null. Right, not at 0, but at Z null. Up there in T3. Got to have that set at Z null. And that should align now. Now notice, perfect alignment. Now it falls on top of my surface. I knew that didn't look right. Right, but those are my level curves that are being plotted out in this domain. And notice that, you can see that two crossing there right in the center. What are those? What's going on there? And you can certainly see that in the illustration. There is that one perfect level where they intersect nicely right there in the center of this surface, folks. All right. We can look at some others. We want to look at H. Look at H. H's domain concern here is the x plus y. All right. What's the constraint on x plus y? X plus y cannot equal 0. Notice how I made that not equals. It's exclamation point equals. Followed by 0 will turn over to not equal 0. And again, that is my constraint equation. And it is excluded. So we use a 0 on the include. Now, was unable to solve with exact, and you're going to run into that every now and again. Just ignore it. Typically, it still solves. It just doesn't do it exactly, right? It does a really refined decimal, though. But here become my level curves. Right? Here they are illustrated in my picture, right, in my surface. Right? Remember, this was the illustration where the parametric plot does a much better job. If we were to actually zoom in to a layer of -2 to 2, -2 to 2 for our x and y bounds, right? The 3D plot shows us one bit of illustration here, whereas we get a little bit more of a refined illustration here, folks. There is a bit of a difference when you start to zoom in with the parametric plot. Right? If I wanted to add more layers to this plot, I could certainly do that by, this is what this part of the program was. I could add, we could do 5 layers above and below Z null. Right? And we could leave their difference between 1, or maybe we make their difference 1/2. Right? You could look at that, respectively. Right? There's now 5 layers above and below, with a difference of 1/2. Right? All initially at a height of 4. I could drop that height by dropping my Z null value. That red line is at 4. Maybe I drop that down to 1. 1. And there you go. You can see there's your level curves plotted in that space. And here they are actually on that surface. Right? Parametric plot doing a much better job at that illustration. Right? With those level curves. Now, this was an interesting case, because the limit at 0, 0 did not exist. And that was because these approaches that are being highlighted on these level curves at 0, 0 all illustrate different heights. And we can show that with a little bit of a limit analysis here, folks. What the last bit I'm going to add to this graph is I'm going to add an approach point, x null, comma, y null. All right. Maybe we make that the coordinate 0, comma, 0. All right. This is going to be the coordinate of approach. All right. In a limit, for instance. We're going to come down here, and we're going to add a bit we're just going to call the limit approach analysis aspect. First of all, we're going to plot. It's going to be actually a list plot. X null, comma, y null into two-dimensional space. Let's go ahead and do a plot style with that. Let's add the directive. Let's make it green. And let's give it a point size. Maybe 3% of the graph. Is that's probably too small. We'll see though. And then we're going to call this plot. We've already done plot 5. I think we're on plot 6. Yeah, because we had plot 5 down here. So we're on plot 6, and I'm going to layer this in to my domain graph. This is my domain plot right here. So we'll call that plot 6. Let's see what we get. Certainly there it is in its space alone, but okay, there it is. It plots that green dot. That's our approach. Our point of approach may be in a limit. And notice how those level curves all behave at that point of approach. They all converge on that point of approach. All right? When that happens, our limit doesn't exist there. Each one of those level curves shows that on those different paths, we give a different output in terms of output behavior. On each of those paths, we're approaching a different layer or value of z is what we're highlighting. And we can actually show that in our graphs here three-dimensionally by maybe putting in a vertical three-dimensional line that's actually at 0, 0 in the domain. Right? That runs the extent of this three-dimensional graph. And you will see it actually passing through all these level curves at that one location. Right? At that one domain concern. So that's maybe the last thing I'll add up here. Let's call this plot 7. This is going to be a parametric plot. 3D, because it's going to happen in three-dimensional space. It's going to happen at x null, y null, and the z values are going to vary. And we got to set some bounds on those z values. Now we're going to make these adjustable because these are a little hard to set so that they change. So I'm going to call them m and n. And maybe we have those. Usually what you want to do is you want to go down and look at your plot and say, all right, I want these z-bounds to go from -5 to 5. That'll fit this entire space you'll see here. So let's set those m and n values at -5 and 5. Right, the overall plot range, right, we might see going on in our graph. And that's going to make a parametric plot of that in vertical line and, well, parallel to the z-axis line at the coordinate x null, y null. And let's actually drop that. First of all, let's call it plot style. Let's just make it green. I don't think we need to change its thickness any. And let's lay that in here into these three-dimensional plots. That's going to be plot 7 there. And that's going to be plot 7 there, if I'm correct. There we are, folks. All right. That vertical line, and it's actually a little nicer down here, it shows us where that domain concern would be from above. But running down through our surface And what we see is each and every one of those level curves, it's really highlighted here, you can see passes through. I could even zoom in if necessary, right? See, each and every one of those level curves passes through that vertical constraint, or well, that one location where x comma y would be equal to 0 comma 0, folks. All right? Each and every level curve intersects that location, all right, along that curve. So every one of those will give a different approach when we approach 0, 0 in the domain. Every one of these approaches of that location in the domain will give us a different output value for z, because they'll be falling at different values of z up and down this green axis. All right? That is what this graph or this analysis is showing us. All right? If I was to move that out to the location maybe of 1 wouldn't work, but we could 1, 0 would work. Let's turn off the plot. The list plot. Let's turn everything off we don't need. We actually don't need any of that stuff above. So like I don't need this table. I don't need that table. I think that's everything. Right there is where we're now going to approach. And on that one approach, there's only one output, and that's going to be 0. Or, sorry, 1, wherever the red line happens to fall at. You can plug 1 comma 1 into this function and see that, yeah, it's 1 over 2. It's going to be at 1/2. Oh, sorry. Y is 0. X is 1. So that would be at 1. Right on that red graph where we'd expect 1. If we look at that line through our graph here, folks, it only intersects one level and one level only. So that limit exists. Any path passing through that point in our domain will intersect this surface at just one location, right? It'll just go to one location on that surface. Unlike at 0, 0, it fell at many locations at one point in time. At one location that was an exception and wasn't included in our domain. That one domain concern there. All right? Some uniqueness. This adds to some of that limit analysis there, folks. All right? So is there anything else I want to do here? We maybe ought to define our adjustables, all of our adjustables at the very least. This is our z-bounds. Right? This is our red level curve location. Right? This is number of levels above and below z null, right? It's going to be our number of levels above and below z null that we want. And this is going to be the difference in z between each level curve. Right? We had that set at 1/2. We could go back and set that to 1. Maybe we only want to look at 3 levels, or 3 levels. Remember, these z-bounds were actually used here in our limit approach analysis, folks. You're going to want to adjust those according to the z-axis in your 3-dimensional plots. From -5 to 5 was a good adjustment here. Right, I think that was it in the adjustables. That's everything we oh, and this is our box ratio settings. in 3D plots. Right? Use 1-to-1-to-1 or automatic. Right? Either of those will work. Folks, we'll add that to the code here. All right. Let me save this before I forget. And I think that is our program, folks. That does a nice little analysis for us. Right? Shows us level curves, shows us domain, shows us the level curves in the domain. Right? We even can add points of approach to kind of visualize those within that region of the domain. And then it also plots all that out in three-dimensional space, which is all very, very helpful when having to do a bit of limit analysis. How is this surface behaving as we approach this one location on it? And what we notice is that there's only one point that we're approaching as a z value for any given xy value in that approach. Very different, right? And notice the level curve behavior. We only have one level curve converging on that location. Whereas if you look at the location of 0, 0, right? We do get some precision issues. Just ignore it all, folks. Oh, wait. It did botch that. What did we do? Oh, you can't have bounds from 0 to 0. Wrong location. That's -5 to 5. Here's where I wanted to change things. 0 to 0. Da, 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 da. So that's now that location. And all these level curves are converging on that one location. They're all showing that depending on your approach, or if you're approaching on this curve or that curve or that curve, you're going to hit a different height along this green line. Limit doesn't exist there because of that. All right? Limit analysis, folks. Oh, looks like my volume was playing there the whole time. Hopefully it recorded. I don't want to spend 3 hours going through this demo. But I am done, folks. Maybe I'll do a slow scroll through it here so you can read it. Can I zoom out a little bit so it's all there nicely on the screen? I'll start at the top. I'll dip into the background. And then just kind of slowly scroll down. So you can slowly take in the whole program. Right? We added this first part for the limit approach analysis and this level curve analysis. We added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lines of code here, folks. And did some adjustments a few other locations. Particularly down here in this show command for our domain. And we added these show commands for our 3D surfaces. All right. Hopefully you're all doing well out there. That is my Mathematica demo for, again, multi-dimensional functions, kind of doing a plot analysis and looking at a domain analysis with level curves. And hopefully that'll help you get through calculating and examining limit values, folks. But with that said, I am done. I'm done for the night. I'm going to still got to get some more videos out to you, folks. But that's it for now. And I'll see you in the next one.